Now we move to view this group action as uh, as a group homomorphism from the group G into the group of permutations. So this can be viewed as an homomorphism, from the group that we have considered, from G uh, to the group of permutations. Okay. So let us have a look on this discussion. So the theorem is that the theorem is that let X be a G set. So X be a G set means you have already in your hand a left action of G which acts on X. Then the left action of left action dot of G acts on X will induce a group homomorphism from the group G into the group of permutations curly AX. So into the group of permutations curly AX of X. So thus this theorem says that the left action of G which acts on X can be viewed as a group homomorphism from the group G into the permutation group defined on the set X. So that means for any group action you can have a group homomorphism from G into the permutation group of X, that is curly X. And in the reverse case, if you are considering a group homomorphism from G into the permutation group curly AX of a set X, then it will definitely give you a left action. So let us have a look on the proof of this theorem, how to define the group homomorphism. So that is our aim, using the left action of G that acts on X. So now first of all, let us consider an element, an arbitrary element, small g belongs to capital G. And once we choose this G, it is fixed. Although we have chosen this G arbitrarily, but once we choose, it is fixed now. Now, we define a map which has been indexed by this element G, that is tau G. And the map will be defined on the domain X into X. That is, tau g will be a map from X to X defined by, what is the definition of this map? That is tau g at X. So the functional value of this map will be the element g dot x. That is the image of the left action, which left action of small g that acts on small x, that is g dot x. So this is your image, and since dot is the left action, so g dot x is a member of the set x. So let us have a let us check that is it a permutation on x, that is it a bijective map on the set capital X. So this is your claim. What is the claim? The claim is that tau g is a bijection on X. So this is a very easy checking to show that tau g is a bijection, because now let us consider two elements x1 x2 from the set X, and suppose that tau g x1 equal to tau g x2. So we have to show that tau g is 1 1. So then it is g1 dot x equal to g2 dot x. Now someone may feel that we shall cancel x from both sides. It will not happen, because we are in the set X. So this is not a algebraic structure at all. So g dot x equal to g1 dot x equal to g2 dot x. Sorry. I have wrongly written. Sorry. Yeah. So this is g dot x1 equal to g dot x2. Yeah. So someone may feel that we can cancel this g from both sides, but this will not happen, because this g dot x1, g dot x2, these are all members of the set X, which is simply a set. Okay. So what to do now? In our hand we have the left action, and we have the property 1 of the left action, that is, it will satisfy the property 1, the axiom 1, that is, now to use the axiom 1 we need to consider the inverse of this g. So we shall act g inverse on these elements. Now using this action and the axiom 1, so you can write down it as g inverse g dot x x1 equal to g inverse g dot x2. Okay. Now what will happen? Now g inverse g is e dot x1 equal to e dot x2. Now by property 2 of the left action, that is, e dot x1 is x1 and e dot x2 is x2. So this shows that if the images are same, then the points will be, then the elements will be same. So this implies tau g is 1 1. Now to check that it is onto, so let y belongs to x. Then
স্যার আপনার কথাগুলো মাঝে মাঝে কেটে যাচ্ছে খুব।
আচ্ছা, হ্যালো হ্যালো হ্যালো,
হ্যাঁ ঠিক আছে, মাঝে মাঝে কেটে যাচ্ছে আমার।
আচ্ছা আচ্ছা। So then we need to search out an x such that g dot x will be y. So then tau gx equal to y implies g dot x equal to y. Now we need to solve this equation. We need to find out the x. Now what will be the x? Then just applying the same procedure that we have done in this calculation, that we are we invite G inverse to act upon G dot x. So G inverse dot G dot x will be G inverse dot y, and using this one it will be G inverse G dot x equal to G inverse dot y. Now G inverse G is E, so E dot x is G inverse dot y. So that means it is x equal to G inverse y. So this is your point which will map to y. So this means tau G is onto. So thus we have shown that the map what we have defined on x is a bijection. So hence, so since it is a bijection on x onto itself, so tau G is a permutation. So hence tau G is a permutation defined on x. So this program says that consider any element of the group G, you can define a tau G. So each element of G will give you a permutation on X. So thus this will set up a correspondence between the group G into the set of all permutations on X. That is, so this says that one can correspondence for each G belongs to G, a permutation on X. Permutation on X which is tau G. So hence we define a map denoted by phi colon G to curl D AX. Now since we know that the permutations on the set X will form a group with respect to composition of mappings. So this is a group and this is also a group. And what is the definition of the map? So this will be defined by phi of small g will be the tau G, where we need to define this map again. So tau G at X will be G dot X for all X belongs to capital X. So thus this defines a map from the group G into the permutation group called X. Now it is so we have to check that this phi is a homomorphism. So for this reason, so let G1, G2 be two elements of capital G. Then what is phi of G1, G2? Phi of G1, G2 will go to tau G1, G2. Now what is tau G1, G2? Where tau G1, G2 at x, it will be G1, G2 dot x. Now using the axiom 1 of the left action, so this will be G1 dot G2 dot x. So this can be written as, so it is, so G1 acts on G2 dot x, so I can write down it as tau G1 of G2 dot x, and again since G2 acts on x, so it can be written down as, so tau G1 of tau G2 x. So that means tau G1 compose tau G2 of x. Now since this is true for all x belongs to capital X, so these two functions are equal. So tau G1 G2 equals to tau G1 compose tau G2. These two functions are same. And hence, so phi of G1 G2 is tau G1 G2, and it will be equal to tau G1 compose tau G2. That means it is phi of G1 compose phi of G2, and this says that phi is a homomorphism. So this says that phi is a homomorphism. Homomorphism on G into the permutation group curly AX on capital X. Okay. Okay. So now with the help of this theorem, we shall have the theorem which is due to Kelly's theorem, which is uh, familiar to us because we have already uh, discussed in the which semester, maybe second or fourth, something. No, second, right? So Kelly's theorem. What was the statement of Kelly's theorem? That is, every group G is isomorphic to a subgroup of a permutation group curly AX for a suitable choice of set X. Every group G is isomorphic to a subgroup of a permutation group curly AX for a suitable choice of X. This. So we can prove this theorem using group action. So this shows that group action was there at from the beginning. Although we have not noticed that the group action is actually works behind those facts. So what is the statement of that theorem? Kelly's theorem. That is, a group G is isomorphic to a subgroup of a permutation group curly AX, where curly x for a suitable choice of set X. Choice of set X. So we are to prove this theorem using group action. Now the choice of X, it is very important here. Now for the proof of this theorem, we shall consider, so let X has been chosen as the group G itself. So this is our natural choice. So let us consider X is G. So using this one, now we can define a map which can be regarded as the left action. But what is the map? Since we have chosen X equal to G, so the map will be the binary operation itself which the G has. That is, here the action is G dot A is GA. So this is your action. That is, dot is the binary operation which the G, which the group G has. So this is your action. So therefore, G itself is a G set. So G itself is a G set. So now, so by the above theorem, since this is a left action, this action is a left action. So by the above theorem, we can say that this action will induce, so this action of G on X on G will induce a homomorphism. A homomorphism phi from G into the permutation group of G, because we have considered the set as G. So we'll induce a homomorphism phi from G into AG. Now it remains to show that this phi will be 1, 1. So to check that it is 1, 1, we need to consider its kernel. So what is the kernel? So now car phi. What is car phi? Now car phi is the set of all those elements of the group G for which the map phi, that is phi of G, will be the identity element of this group. Now what is the identity element of this group? It is the identity map, that is identity map on G, and this shows that set of all G belongs to capital G. So it is tau G equal to identity map on G. That means set of all G belongs to capital G such that tau G of X equal to Gx, but Gx will be X because we have considered the identity map. Since it equals to identity map, so tau Gx goes to x, that is gx equal to x. So set of all those element g such that gx equal to x for all x belongs to capital G. Now since g and x both are in the group, so now we can apply the cancellation law because we are in a group. So by cancellation law, we can cancel x from both sides. So we will have g equal to e. So that means the kernel will consist of a singleton element identity, and this implies that phi is 1 1, and hence being a homomorphism, and since it is 1 1, so phi is an isomorphism from G into the permutation group called AG. That is, so this means G is isomorphic to phi of G image, which is a subgroup of Carly AG. Since we know that if f is a homomorphism from G into G dash and H be a subgroup of G, then fH is also a subgroup of G dash. And for this reason, phi G is a subgroup of Carly AG. Since G being a group, so phi G is a subgroup of Carly AG. And this proves the Kelly's theorem. Okay. Now we need to check practically what will happen for some particular cases that we have proved that every group is isomorphic to a subgroup of a permutation group called AX for a suitable choice of X. So that means every group can be viewed as a subgroup of the group of permutations. So that is, the elements of a group can be represented by some permutations. Okay. So let us have a look on the problem. I should write down it as that show that the Clansford group K4 K4 is isomorphic to a subgroup of S4. Why it is S4? Because we are considering the group K4 which has 4 elements. So G has 4 elements, so the number of elements, so the permutations on a set of 4 elements will be S4, the symmetric group of order 4. Okay, so that is why we are writing down that the Clansford group is isomorphic to a subgroup of S4. But how does it work? So what is the process through which we can represent K4 in S4? That is, we have to represent the elements of K4 as an element of that group, symmetric group. So let us have a look on this. So let K4 is, suppose K4 is EABC. Okay. So where the order of A is 2, order of B is 2, order of C is 2, and This is a commutative group. And Ca equal to Ac equal to B. Clansburg group. But we need to represent this group as a subgroup of the symmetric group S4. Then what is the process? Now first of all, let G equal to E. Just we do the same thing that we have done in the in the proof of this theorem, this one. Just doing the algorithm, this one, that is tau gx is g dot x. This tau g will be a permutation on x. What is x? Now in our case, by Kelly's theorem, what we have observed, that the x is the group itself G. So in our case, x is K4. So the set of 4 elements. So let us writing down it as, so let G equal to E. Then now tau G at E. So tau G will be a map from K4 to K4. So tau G will be G dot E. Now what is G dot E? What is G? G is identity here. So it is E dot E. So that means it is E. So E goes to E. Now tau G A. It is G dot A. That is, it is E dot A. What is E dot A? It is A. So A goes to A. Tau G B goes to B. Tau G C goes to C. So tau G can be represented as the permutation of a symmetric group of order 4. That is the permutation on a group of 4 elements. And the 4 elements are E, A, B, C. That is E, A, B, C. So E goes to E, A goes to A, B goes to B, C goes to C. Now what is the permutation? This is the identity permutation, I. Right? Now we consider G equal to A. Then tau G E equal to G dot E. So that means A dot E. So it is A. What is tau G A? It is G dot A. Now what is G? G is A, so A dot A. It is a square, but A square is identity. Now tau G B, G dot B, that is A dot B, but AB is C. Tau G C. So it is G dot C. What is G dot C? A dot C. Now A dot C is B. So this implies tau G can be written as E A B C. Now E goes to A goes to E, B goes to C, C goes to B. This one. That is, it is E A B C, the product of 2 cycles. Now let G equal to B. Then what is tau G? Now tau G is tau G E, G dot E, that is B dot E, which is B, tau G A, G dot A, B dot A, that is C, tau G B, G dot B, that is B dot B, that is B square equal to identity, and tau G C, G dot C, B dot C is A. So that means tau G will be represented as E A B C. So E goes to B, A goes to C, B goes to E, and C goes to A. So that means it is the product of two cycle EBAC. Again, if G equal to C, then tau G equal to tau G of E. Tau G of E is C dot. So G dot E, and G is C, so C dot E, so it is C. Tau G at A, G dot A, that is C dot A equal to B. Tau G at B equal to G dot B. So B is C, so it is C dot B equal to A. And tau G at C, so it will be G dot C, that is C dot C, C square equal to identity. So that means tau G is EABC, where E goes to C, A goes to B, and B goes to A, C goes to E. So it is ECAB. So thus now let us now it seems to us that you are not familiar with these symbols. But now if we consider E equal to 1, A equal to 2, B is 3, and C is 4. Now the first case is for E. E goes to tau E, and tau E is, so it is tau 1. So what is tau 1? Tau 1 is the map. So let us have a look of tau, this one identity, that is that is 1, 2, 3, 4. 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4. That is the identity map. Now A goes to tau A, that is tau 2. Now what is tau 2? Let us have a look of on tau A. Now what is tau A? Tau A is EABC, product of two cycles. So that means EABC. But what is EA? E is 1, that is 1, 2. What is BC? 3, 4. So this is the permutation. Now B goes to tau B, that is tau 2, tau 3, sorry. And this is tau B is EBAC. EBAC. Now renaming this, so E is 1, B is 3, A is 2, C is 4. And the last case is C goes to tau C, that is tau 4. And what is tau 4? Tau 4 is ECAB. ECAB, that is 1, 4, 2, 3. So thus the permutation representation of K4 is representation of K4 is, what is K4? So this is first identity permutation, and for A it is 1, 2, 3, 4, 1, 2, 3, 4, and for B it is 1, 3, 2, 4, and for C it is 1, 4, 2, 3. So this proves that this is the permutation representation of Klein-4 group in the symmetric group of order 4s4. Hope you understand this representation. In a similar way, I would like to give you the exercise that write down the permutation representation of the group Z4. It is also a group of order 4. It is a cyclic group of order 4, Z4. So you need to represent it in S4. As like as we have done it for Clansburg group in this procedure. Okay.